Thanks. It's a great pleasure to be here. Before starting, I would like to acknowledge my two colleagues to work with me on this topic, Julia and Simone, who works in Milan. And I would like to give also a brief overview of my talk. So basically, what I'm trying to do today is to give a quick review of max table distribution in multivariate dimension. So the first day, Yvette show the most important result, I think, in the linear case about block maxima, which is a convergence toward the general extreme value distribution. And the idea of my talk is to say maybe we can do the same kind of approach in the multivariate dimension case. And to explain that, I'm going to basically look at a specific example, which is rainfall data. And along the way, we'll see how we can go in terms of the estimation, which is an important part of statistics, because here my talk is going to be mostly on statistics. So here I just plot a map of France. And this is from a paper with Armel and Theo Rich, a student we had together. And here is just to show you that if you estimate the shape parameter, I don't going to tell you how we did that, but basically you get this kind of map. And what you can see is like there's some part of France where rain intensity, I have to figure out how to work. You should do it here. Rain intensity here in the north part of France is not very strong. And when you go to the south of France, of course, as you know, it doesn't rain very frequently, but when it does, it could be very, very heavy rainfall. And so, which means that the shape parameter here is going to be fairly different. Like, let's say in Brittany or in Marseille. Okay? And why I show this map too is to tell you something very important here. This map doesn't say anything about the dependence between maxima. Here it just says at a specific location what is the intensity of precipitation. But it doesn't tell you if, for example, precipitation maxima between Marseille and Nice are fairly correlated or not. Okay, so my talk is not to speak about the shape parameter, but it's much more to see how we can measure the dependence in terms of maxima, rainfall maxima in space. And so I'm going to focus even more on the description of the data analysis I'm going to do. Here we are going to look at rainfall again, at every hour. And in the fall season, because in the fall season, basically it's like when you get a lot of water. And also we are going to take a block maxima of basically 1 week. Why 1 week? Because if you look at a storm, it's very rare that the storm is going to last more than 1 week, especially thunderstorm. So basically we are going to assume we have kind of almost independent in time. But in space we have dependence. I put a red dot there because it's my lab. So if you want and you want to have more questions at the end, you can also come to Paris and we can talk. So here now we have a problem. Here we have 92 stations. Okay, that means the dimension of the problem is 92. So we move from d equals to 1 here to d equals 92, which is very big. I mean, at least for extreme value theory people, when d is large, usually it's d equals to 2 or 3. Here we have 92. And so to simplify, I'm going to use what is usually used. I'm going to assume, but it's not a restriction, it's much more to explain in a more pedagogical way. We assume that we have unit Fréchet margin. Okay, so we assume we know the shape parameter, it's 1, and we assume that everything has to be renormalized, standardized to the exponential, to the unit Fréchet margin, where x here is positive. Okay, and if you start from there, that's a univariate case, and what you can see, of course, because we have the max stable property, which is if you take max of unit Fréchet and they are independent, then there will be the same distribution again. That's really the key part of extreme value theory in some sense. And one way to write this down is just to say if I take a power, which means the max of Tx and equals of f of x for this. So this is very obvious. In fact, in this equation, there's something also very powerful. And that's why people use, for example, in computing return level of quantile very far away in the tail. Because what that means here, that means if you are interested by the set, for example, far in the tail, you can and you have observation not in the tail, I mean, in the tail, but not far away, it's not far away enough, but you want, for example, to compute the return level for building a dam or a dike of 100 return level, but you have only 20 years of observation. If this relationship is true, then you can go, by changing t, you could go back from the extremes to the moderate extreme when you have observations. So it's a very, very important property. And that's a property we like to keep when you do multivariate extreme too. And some people who work on that, in fact, there is usually Lawrence Dohan and Sid Resnick work on that. There's a few books here I mentioned. So if I go back to my line in the univariate case, I have this. And so if I want to preserve the max stable property in the multivariate case, I'm going just to say, well, now I don't have, let's say, one dimension, but here m dimension. Okay, but I would like to have exactly the same property. Okay. Another way to see that is to answer the question the following way here too. You could ask yourself here, if you take the component maximi, so now you don't have a z here, only one time series, but you have, let's say, from e equals to 1 to d, for example, the dimension is d. Then you can ask yourself the question, and so this is not exactly true anymore. You have something much more like g of x1 xd. Okay, so there is the asymptotic theory, exactly like the univariate case, who tell you if you get components-wise maxima, then it's going to converge to this type of distribution, which I'll call here f, if it is unit Fréchet margin. And so the mathematical question is, what are the simple properties for this kind of distribution? Well, of course, you can always rewrite this by exponential of something. And if you want to preserve this kind of thing here, that means you can write v of tx equals t minus 1 v of x. Okay, so you have this homogeneity of order -1. Okay, and basically that's it. If you want to model multivariate extreme, what you want is to, if you have data, like I have my data, my rainfall data, my question is, how can I find a v function that satisfies this relationship and also fit my data? Okay? And just to give you a very classical example, you can look at the logistic model. This, for example, it's an example of the function v. And you can see there's one parameter alpha. And if you multiply everything by t, a constant t positive, then you can put out the t out. So this is a valid bivariate extreme value distribution. Okay? But there is, I think it's a very, after it, there is a very important question. This is one example of parametric dependence function for the bivariate case. But now if you move and say, now I don't want to go in the bivariate, but multivariate case, or the infinite dimension processes, you have different approaches. One approach is to say, in terms of statistics, to say, I'm going to impose a parametric form for the V function. Okay? And if you look at work by people who work on the maximal process, usually they like Brown-Restig process, Schlatter process, Smith process, it's basically they impose a dependence function and after they estimate that. So in some sense, it's a dimension reduction. Okay? But in theory, the theory tells that there is not a parametric function. In fact, this is much more the approach when you impose a parametric function, that means you make a strong hypothesis. Maybe it's an advantage in some cases. For example, maybe if you use dynamical system, maybe you can ask yourself, maybe what should be the good V function if you impose a model at the beginning. But in my talk, I'm going to do something very different from dynamical system in some sense, because I'm going to assume that I want to have a non-parametric approach. I don't want to impose anything on the V function except the condition that we have here. Okay? And if you think about it, if my dimension is d equals 92, I have 92 stations, it's going to be almost, it's going to be impossible, because non-parametric family for d equals 92 is too big, the space is too big. So what we are going to do is to first reduce the dimension by clustering our stations together, and then after that, for each cluster, we are going to fit a non-parametric model. So to do that, I'm going to go back to the bivariate case, and here I'm just going to also it's also to see a little better what is this V function here. In some sense, if you take the very specific case where x1 equals to x equals to x1 equals to x2 equals to x, then if you have this, okay, this is now x has become a scalar, and it's x multiplied by the vector 1, 1. So by the homogeneity function, you can put that out, okay, because v of, I don't know if I'm clear. If you have v of x like that, this is with notation like x scalar 1, 1, and so I can put that out because I can use, and this I call that 1 in my notation when it's bold, just in terms of notation. And so if you take the power of that, because we have Fréchet marginal, this is just a Fréchet margin power v of 1. And if you look, if you have the independence case, that's a product, so v of 1 would be 2. If you have complete dependence, x1 equals to x2, then v1 equals to 1. So v1, in some sense, gives you a sense like a correlation coefficient, but of course, it doesn't characterize a full distribution because I don't look at every x1 and x2, I look at the case where x1 equals to x2 equals to x. But still, this is a very, very good summary of what's happening in the bivariate case. And you can do that the same in the multivariate case. So with Armeg and colleagues, and there is a lot of people who have been working on this estimation of this extremal coefficient v of 1. But what we did with Armel and colleagues, we look at a special case where we introduce this distance, which is the L1 distance. In geostatistics, it's called a manogram, but whatever, it's just a L1 distance. And if you look at the special case, if I take mu equals a max combination of f1 of x1 and f2 of x2, and v is just the average of the two, then you have this relationship. So once I'm just going to spend a few seconds to explain why we take f1 of x1, because if you apply to a random variable, its CDF itself is going to be uniform. Okay? So here, this is always going to be defined. So which is good, because maybe sometimes it's not, but here it's going to be always defined. And what's happened, if you can compute this mean, this difference, then you get the extremal coefficient. So a simple way to estimate, now I've given you my data, for example, bivariate observation, bivariate time series. What you can do, you can just compute a mean, basically, and then put an at on that, and then you have an estimation of V of 1. That's a fairly straightforward approach. That's why I like it. But there is many approaches for that. So here, as I say, I have my 92 station. I'm not going to spend too much time on the clustering, but what we did here, we tried to divide fronts in different parts. And so we use kind of a k-mean algorithm. So I don't know if you know what is a k-mean algorithm, but basically, what we try to do, we try to take this distance, this L1 distance here, okay, and then we put point together that minimizes distance, okay. And the difference between the classical k-mean algorithm, the k-mean algorithm usually you compute a distance with respect to a center, which is the average, but we don't want to take the average because the average of max stable distribution is not a max stable distribution. So the difference here is we take one member of the cluster and we compute the distance with the other members. At the end of the day, you can find the details in this paper, but you get this map. And I'm not going to speak about the colors. Here's a number here, but what I want to tell you about that, it's kind of very surprising. Because what we did with this algorithm, if you think about it, we just give to the algorithm the data itself, the rainfall data. We didn't put any geographical information. We didn't give the latitude and the longitude of the station. But the algorithm was able to find coherent structure. Okay, you can see like this cluster here on the Atlantic coast here. Okay, so what I did, I take pair of stations, okay. So for example, you take the rainfall data in Marseille, and you take the rainfall time series in Nice, which is nearby, and then you compute this extremal coefficient or this distance. Okay, so you can do that for all the pairs of around 92, and then you use an algorithm which basically do the following things like this. Suppose you have this, and suppose you have this at the beginning. You don't know they have two clusters, but here I make the graph obvious. So you pick up at randomly two points, let's say these two, and then you compute the distance between each, like you say, we have two centers, and then you group, you say, oh, this is this one, maybe this is this one. Okay? And then after you compute the mean distance about all these points, so maybe the next point is going, now this center is going to move it here, and then you repeat the algorithm, you compute the distance and that, and then you compute the distance, and you say, oh, this point now should belong to this cluster. And you repeat like that the algorithm. And I can speak about that more about that later on, because otherwise I won't have time. But basically, what you get cluster of time series who are coherent in space. And now what I would like to do is to say, well, here I have 7 stations, here I have 7 stations, here I have 7 stations. So now I reduce my dimension to 7, okay, because I want to make comparable things, so everything has to be 7. And so now the question is, within this cluster of 7 time series, okay, can I compute the V function in dimension 7? So some of them, there is other points like here who have been removed because they couldn't be attached to a very strongly to the cluster. So, so now I'm going back to the problem of dealing with the function V, and you have different approach. In fact, basically you have 3 different approaches. One is to say I can try to estimate V directly. Okay, that's one option. Or you can use a spectral measure, which is a different representation of the V function. Okay, and so I'm going to write down. So either you can, if you want to have V, you are asking the question, what is V for my data? So either you can say, I'm going to model that directly, or you can say, I'm going to use the spectral measure DH, and that will give me V. But you have to integrate over this set here. Or you can rewrite V as this function. And not here, I don't have an X anymore, but I have a W. W, it just means that so suppose I take Paris, my time series in Paris, and one in Marseille. And so it's rain. And sometimes it's going to rain, very heavy rain maybe in Paris. And sometimes you have heavy rain in Marseille. Sometimes it's like this, whatever. But because Marseille and Paris are very far away, it's not very likely that you will have a lot of points here because it's not going to rain a lot at the same time in Paris and Marseille. So what you can always do is to draw a line like this and to project this point on the line. Okay, and then if you look at the distribution of the points here, basically this is kind of a, so this kind of distribution, roughly speaking, because I don't have time to mention what it is exactly, but basically it corresponds to the S function. Okay, and so if you do that in 3D, if I add, if I take Paris, Versailles, and Marseille, you could do the same graph, and you can project on the simplex. Okay? So you look at the density of points above a certain threshold, which is very high, basically, and you look at this. And so if Paris and Marseille, Paris and Versailles are close together, so you will have a lot of points here. And here we have the point here, the crossing. It's like you have a, you know, at the beginning of the week, it was Bastille Day, there were fireworks. So it's like you're a firework, and then you look at the direction of the firework. Okay? So that's a very quick summary, but so we have 3 different strategies. And what we are going to use is going to use this strategy here with the function A. Okay, and what I would like to also mention here, oops, if A equals to 1, omega is just, so you have a R equals x1 plus x2 plus xd, and then you define omega as a ratio of xi divided by R, basically. And so the sum of omega equals to 1, and so that's why it lives on the simplex. So if you take A equals to 1, that means here you have 1 over x1 plus 1 over xd. And that's the independent case. Remember? We have unit Fréchet margin. So in the case where it's independent, it's a product of the two. And so it's just this. So when A here equals to 1, we are in independent case. Okay? And in fact, when x1 equals to x2 equals to xd, you have this gray triangle here. That means we are in the dependent case. And then we can be between the two. Okay, so it's so of course you could do that in 7 dimensions, but I cannot show the picture. And so now the question is, do we have something like the red one or the green one or something between? But look, there is a special also shape. The shape of the distribution A has to always to be convex. Okay? And you cannot have also shape of A cannot go under that. For example, A cannot do this and go there. So A has always to be convex. He has to go through the endpoint here, and he has to be in the triangle. So in some sense, you have different constraints. We have this constraint here. So I say A can be anything, but he has to obey this constraint, okay, which is important. So, so I'm going to, you have to remember that, but you just have to remember the picture. If you remember the picture, you should be fine. All A function has to be convex and they have to be in the triangle, basically. So we have 3 conditions. I'm going to call them P1, P2, and P3. So the first thing we are going to do, I'm going to take the same idea I had before, and this I'm going to speak quick. And then I'm going to find an estimate. Like here, it's a description in 3D. So if I take an estimate of my V function, I get to something like that. I'm going to explain later on what I got that. But here, in this triangle, so basically the triangle is kind of the simplex in 3D like that. So what you can see, we have an estimate of the true function, which are the black lines, and you can see that's the estimate. There's a problem here in the sense that it's not convex. So we have to figure out how to make it convex. That we like to have that. In fact, there is some people in the room here who have worked on this issue. For example, Armel and worked with Amélie on this in 2008 with Johan. And Johan also worked with Gordon on this question of how to project an estimator to make it obey the 3 constraints. We have P1, convexity, the fact you have to have the constraint P2 and P3 too. The limitation of the method, which was good in some sense, but there were a few limitations, at least for us, because remember, we have cluster of 5, 7. Okay? And in the paper here, the strategy they have is to say, well, we are going to work with basically the edge function. We are going to make it an expansion in a discrete spectral representation. And then we'll get back the function A. Because if you have A, you have V, basically. Okay? And that's fine. But to do that, you have to make a grid. You have to, in practice, you have to make a grid on the simplex. Okay? And so the number of points on this fine grid, depending on the K, which K is the quality of the approximation in some sense, it's in order of KD minus 1. So if, for example, you have k equals to 10 and d equals to 7, that's 1 million point. And in practice, and then after you have to compute integral over that usually with this algorithm. So in practice it's good for d equals to 3, but for d equals to 7 we couldn't do anything with that. And also we didn't know how to get confidence band. That was another problem. But so we opt for another approach. But first I'm going to speak about, if you want to do the projection, you need a first guess, okay? And because we like to work with the monogram, first which was good in 2D, we are going to do in the multivariate case. And so remember that was in the 2D case, but you can have the same idea here. But now in terms of taking U and V equals a bivariate, you can get a max stable combination, okay? So here again, I take the F, the CDF of the function, I apply it to X, which is make a uniform. I take a power, take the max of this thing, and I subtract the mean. And so if you compute this difference, you can get back the V function, because this, it's a one-to-one relationship with this distance nu of omega. So in other words, if you know how to compute this, you can just get A. Okay, and this is nonparametric. Okay, it's just one estimator. There's many different estimators possible, but we use this one. And so if you want to estimate that, well, now we have an expectation. So you have 1 divided by n. You sum over all your observation. You F, usually we don't know what is F, the empirical distribution, but we can replace it by the empirical distribution. And this gives you basically ranks, okay? And so this is a very non-parametric estimator. And then you get this estimator here. So nothing very complex here. It's just you compute basically a mean, you inverse it, and you get an estimator. But this estimator doesn't obey the constraint. Necessarily it could, but it doesn't. So we have to make it right. To do that, we use what is called the Bernstein-Bézier polynomial. So why we use this family? Because there is a lot of family of Bernstein polynomial, and we choose the Bernstein-Bézier polynomial because when d is greater than 2, it preserves the shape of the estimator we want to use, of the projection. So here we have some constraint. We want, for example, convexity. So we want a base that preserves convexity. So here, if you have never seen Bernstein polynomial, for example, in case of d equals 2, this is close to a binomial distribution. In fact, it's a binomial distribution. So you can extend it in the multivariate dimension, and you have this formula here. What's important for us, it's like BA, with A, it's our Peacon's function we want to estimate. We can, for different expansion, we can write it down like this. And so the game, the game is to say what is beta. Here you have beta L. We have to estimate this. That's what we need to do. So I'm going to skip that because I'm running out of time. So let me summarize what we do in practice. Maybe that will give you a better idea. So first we have to transform our data like this to get the omega. And then we get a first guess, like the monogram estimator in the multivariate case. Then we have to project with the Bernstein polynomial. And then we would like to solve this equation. That would be perfect. But of course, it's not possible. Here, what we need to do, we need to do a nested approximation. But what's nice is for any k equals 1, 2, 3, 4, 5, the larger the better. After, it's a computational issue. But basically, all the time, you are sure that your estimator is going to be convex and also obey the two other constraints. So let me give you a little bit more detail on that, if I can. So basically, our estimator at the end is for a given k will be of this type. So again, I'm going to speak about the practical issue here. What's nice about this constraint here is you have to find ck. But ck is just a matrix, and this matrix doesn't depend on the data. So when you do it once, it's done for a given k, given d. So after, the algorithm can be run many times. Also, it takes a lot. I mean, it takes quite a bit of time to find this condition. You have the condition at the boundaries. Remember, you want to go through. We want to be in the triangle, and we want to be at the, in the triangle of A like this. So this gives a second matrix C, and then we have a third condition. We want to be at the endpoint, okay? And then it gives us the condition C3. So we have three different matrices. We put them together, and then we just have to solve this. So here, this is from the paper, but it's pretty heavy. But what you have to remember, if you remember your class you took in linear regression, here, what you take here is a basic. Here it's basically the linear regression coefficient from classical regression. And then, because you have the constraint, you have to add this extra term here, which is based on the condition we have. But basically, it's a linear regression problem with a quadratic programming solution. So we can get that fairly quickly. So not the main difference with what Johan did is like we didn't do this. We didn't say we are going to use edge and after we are going to integrate. We just fit directly A. And so here I'm going to show you some results in d equals to 3, for example, and to see the influence of the k. K is a degree of the expansion. So if you have a lot of computer power, you can get k equals to 10 or 20. But for example, here for k equals to 5, the true, what we are looking for, it's a black line, and the dotted line, what we get. So it's not that bad, you know, but still, if you get k equals to 14, it takes more computer power, but you get a better approximation. Also, you can say, well, is it just a big deal to do the projection? Is it? I mean, theoretically, we would like to have something that obeys a constraint, but is it going to improve anything? Well, for example, if you take a logistic model that we saw before, it's just a parametric family you know about, and you take the Al and Tajvidi estimator, so another estimator, and if you look at, for example, a sample size of 200, here you have the mean integrated square error is 5.25, and here is divided by 2. So to project also improve the mean square error. I'm not going to spend time on this table, but basically that's it. In terms of confidence band, which is I think an important question in statistics, it's how to get this confidence band. And so what we did here, we did some bootstrap on the omega, and then on the bootstrap sample you can compute A, the manogram estimator, and then you can project it, and then you have the beta coefficient. And then you can also bootstrap, I mean, you can use a bootstrap betas to construct confidence band, and after you get this kind of thing. Okay. We tried the other option, which was just to bootstrap on the observation here, and then after get the A hat and and compute the confidence band on the A hat. But it was not working very well. In fact, using the beta improved very much the algorithm. So here, for example, it's in d equals to 2. You have the truth in red. And you can see that, of course, we are in the triangle. Of course, we go to the endpoint. Of course, it's convex because that's a constraint we had. But the dotted line are the confidence band. And basically, you can see that the true, it's within the confidence band. You can do that also in d equals to 3. This just gives you nice pictures. But you could do that in d equals 5 or 6 or 7, whatever. It's for the confidence band for the A function. The A function is basically the V function, but expressed on the simplex. So it's, if you have the A function, basically you can compute anything after in terms of the distribution. Yeah. Well, in fact, what's kind of surprising, it's the A function, the estimator A hat, in some sense, obeys a constraint. And so this object is also through Picon's function. But maybe I will come back to that later on. Also, another way to see that is what's called the coverage probability. It's to know, like here, the coverage probability should be 95. And when the way we compute the confidence band, at least for this logistic case, we get basically a little under 95, but not that far, which is not that bad in some sense. So let's go back to our example. So all that for this. Remember, we are looking at cluster of size 7. So for each cluster, we have the A function, the A estimate so what means we have the full distribution, okay? But obviously I cannot show you that because it's a 7-dimensional object. But what is always possible is compute the extremal coefficient here, okay? And that's the colors here. So now we can spend a little bit of time on this scale. So remember, at the beginning of my talk, I show you the shape parameter C, and I say just the intensity. Now this picture here is not about the intensity of the precipitation at all. It's just about the structure, the spatial structure of the dependence among maxima, weakly maxima. And so you can see when you go here in the north, basically, you get around 2.5, 262 and so on. And when you go in the south, you get something higher. Okay? So when this extremal coefficient is higher, it means there is a weaker dependence. Okay? And now if you go back to rainfall data, it's not surprising at all, because if you look in the south of France, the type, the structure of the events are much more thunderstorm. Okay, so they are very localized because of the orographic effect, because of the influence of the Mediterranean Sea, because of the influence of the mountains. So you expect to have very weak spatial structure in this region. But if you look in the north of France, what's happened when you have a big storm? Usually it comes from the west or the north, but it's a big front. Okay? And so there is a lot of strong spatial coherence. And so that's why you expect to have a small extremal coefficient. Okay, so in some sense, we are fairly pleased with this map because it shows that the dependence, the spatial dependence among maxima in a d-dimensional space were coherent with the physical process. So I didn't speak a lot about convergence results. In fact, if you go back to the estimator we looked at, basically everything was based on ranks or the uniform distribution. And basically, a lot of people have been working on what's so-called empirical copulas, which basically is ranking of multivariate structure. And there is a lot of result. And maybe, I don't know if Joanne is going to speak about that or not tomorrow, but we'll see. In terms of the projection, if you take an estimator and then you want to project it, you can look also at the paper by Amélie, Armel, and Johan. And if you want more details about the convergence result for the spatial estimator we have, you can go on arXiv and find our paper. So I'm almost done. So what I would like to do in the future, at least for this application, is to do simulation with a non-parametric Pickens estimate. So what I would like to do is to say, well, if I'm able to describe fully the dependence structure with a non-parametric estimator, it would be nice to even simulate from this non-parametric estimator for many different reasons. And we are able to do that in 2D, but we hope to do that in any dimension. So my conclusions are about the multivariate max-stable vector. I mean, here just a very, very small glimpse. There is a lot of people who have worked on that. There is a lot of open question. I think to me the question about parametric versus non-parametric is always an interesting one. Of course, there's a lot of question about dimensional reduction, spatial temporal, non-stationarity, and so that. If you want to know more about extreme value theory, you can look at the journal Extremes. We have the editor here and the future editor here, and the former editor here. So also, if you want to go to some conferences, if you want to learn maybe more about the weather, the climate, and statistics, and if you want to stay in France, and you can go in Avignon, that's a nice place. Also, you can go to Besançon. The weather is not as good, but you will have more extremes. And if you're ready to take the airplane, you can go to Michigan next year. And there's a big conference on extreme value theory. And I'm going to finish my talk with one quiz for you. Who says this quote? So I'm not going to read it, but you can read it if you don't have any question. But also, it's also a way to, I think, to thank the organizer for putting these two crowds together. I think it's very interesting. So thank you.